Probably one of the areas that the majority of our folks had trouble with was determining experimental correlational survey designs and how to analyze them. A lot of folks were saying that they were doing an experimental design, but then in their analysis section they were running correlation tests, or saying they were doing a correlation, but then they were running t-tests, which are part of experimental and quasi-experimental designs. Which it's completely understandable. This, for a lot of people, this is something very new. So we're just going to go through it again to maybe just simplify it a little bit to make sure that you guys can understand these, not just, for your success on the paper at the end of the course, which of course I want all of you to be very successful with that paper, but also these are very core concepts that you'll need to know for your comprehensive exams, for your thesis, your dissertation, and just, being a graduate student in general. This is kind of the backbone of what we do. So starting with experimental designs, if we just take a second to look at this little cartoon, comic strip, whatever here, got our little fish swimming around, enjoying his life, and here's our researchers with a magnet. Our researcher says, let's see if the subject responds to magnetic stimuli, administer the magnet. And our next frame, we see the magnet whacking the fish in the head. And finally, sadly, in the third frame, our little fish has moved on to a better place. And our researchers say, interesting, there seems to be a significant decrease in heart rate. The fish must sense the magnetic field. Well, looking at this, we know that the fish and his heart rate, ending, and the fish dying is not a result of a magnetic field, but the result of the fact that here's this guy with the magnet who actually injures the fish with the magnet, and that's why our fish is gone. Now, what does this have to do with experimental design? When we're doing experimental design, we usually want to control for all of these factors to make sure that what we're measuring, say we're using a new reading program for our students and we want to raise their test scores. Well, when we do our results at the end, say we put in our reading program, and then at the end we get our scores and our scores don't change, or our scores change significantly, we want to make sure that those scores changed because of our reading program and there's not something else out there that's causing that to change. So in the case of these guys here, they're doing their study, they're thinking the magnetic field is what kills the fish, when they're not paying attention to, yes, the fish's heart rate went down, but it's not the magnet that caused it, it's the fact that they hit him with the magnet. So that's a very, very gross simplification of that, but just to kind of explain the logic behind why we're doing this. So whenever we're looking at we talked about a lot of different types of experimental designs. We have randomized experiments, and that's a true experiment. That's, think back to middle school science where you had your control group and your experimental group, and, maybe you were working with, growing plants or something, which is not nearly as messy as working with people, because people are social animals and things get complicated, which is why we're going to talk about our internal and external forms of validity later. And so is random assignment used? Yes, we use random assignment. Random assignment means that we have our random sample of who we pulled. Random assignment means that of our sample individuals, each one had an equal chance of being put in the control group or in the experiment group. They didn't self-select, and self-select means that the participants choose which group they want to be in, because then you have to wonder, okay, well, maybe they had a particular interest in this already, and that's why they chose to be in that group. Different things like that happen. So we have our, is it a randomized true experiment? Yes, if random assignment was used, each one was assigned to a group. Say you have a class of 50 students, and you randomly, for every student that came up, you just randomly pulled a number out of a hat. Number 1 means he goes into control. Number 2 means he goes into treatment. If you didn't use that, then we move on to the next step, because it's either a quasi-experiment or a non-experiment. So is there a control group or multiple measures? If there is no control group and there are no multiple measures, and by multiple measures I'm talking about a pre-test and a post-test. So if there's no control group and there's no multiple measures, then we can't really say what's causing that thing in the middle. What's causing this thing to happen? Is it our treatment? Is it something else? We don't know. If it doesn't have that, we can put it under non-experiment over here. If it does have that, then we're kind of falling more into quasi-experiment, which is what most education research is, and I'm sure it does appear in exercise science a fair bit. And this is just basically, I mean, people are complicated. When we're working with students, we can't create an entire school and then randomly assign random students into these different classes. We kind of have to work with what we have. There's class A with class A teacher has the students that it comes with at the school, and class B has whatever students it comes with at its school. We can't really shuffle those around all the time. A lot of times we might not have a control group. So in terms of education classes, say we want to see what effect does lunch have on, a full lunch have on students. Well, we can't have a control group that receives no lunch. We can't, you just can't do that because we're working with people. We're not working with plants where we can deprive one of fertilizer or something. So that's where quasi-experimentation comes in. And what I really want you guys to get out of this is the difference between these two. We have random selection for our sample, and we have random assignment. We have a true experiment. That's a true experimental design. Quasi-experiment is where we don't necessarily have as much control, but we're still doing that pre-test and that post-test, so we can kind of establish where they are at the beginning and where they are at the end, and that helps us determine what's going on in the middle. If we don't have that pretest at the beginning, we don't know where they started. So we don't know if it's our treatment or something else that's leading to the results. That's more long-winded than I wanted to be on that. But so let's look at this experimental design chart. Again, these slides are not my slides. These images were from elsewhere, but we'll work with them. So in this particular one, don't worry about all this stuff over here, but we establish our hypothesis. This is what our experimental design is going to look like. And in your final paper, please feel free to put in diagrams. A lot of times diagrams help students understand what's going on, and then they just provide a narrative that that explains what's going on in that design. And it also helps an instructor or your committee chair understand what you're doing a little bit clearer than reading through it, because sometimes for people that are not totally absorbed in your project, it takes us a little while to catch on to all of the parts you're doing. So this really helps. Anyway, I digress. We have our experimental group and our control group. So this is an experimental design. And say maybe here we're looking at what effect does peanuts or protein or something, I don't know what they're looking at here. What effect does that have on the recall score? So peanuts, we could say eating the peanuts, whether or not they had the peanuts is the independent variable. The recall scores are the dependent variable. We're looking to see if these are going to change dependent on what we gave them here. So experimental group, we give them some peanuts, we give them a list of words perhaps to study, and then we ask them to recall those words and we collect their scores. With our control group, we put them into here. Instead of giving them the peanuts or whatever, we give them a placebo. Say maybe we give them, I don't know, we could maybe not give them anything. We can give them something fake. We don't, it doesn't really say here, but you get the point. And then we give them the same study list. They study the words, and then we collect their recall scores. Now we have scores from our experimental group that used our treatment, and we have scores from our control group that did not use our treatment. So we have these two scores. Now this score might be 100, this score might be 95. If we look at that, we're like, oh, 100, that's more than 95, so these guys did better. Not necessarily. We go in and we have to do our analysis, our t-test or our ANOVA or whatever it is we're doing at, depending on our experiment, to determine what that is. And why we do that is, for example, say somebody says the average number of, there's 97 heart attacks on average in, say Canada every year. I know it's way more than that, but just work with me. Follow me on this. And in the United States, there's an average of 300 heart attacks a year. And then people say, oh my gosh, there's more heart attacks, like 3 times more heart attacks in the United States than there is in Canada. Not necessarily. The United States population is 10 times that of Canada. So if we just compare those two numbers, we're not getting a very accurate result because the two populations are very different. One has a lot more people than the other. Other things come into play there. So in order to take all of these things into consideration, instead of just looking at these numbers, 195 at face value, that's why we go and we do our statistics, because our statistics will take into account population and sample size and all that good stuff. So that's where we're going to go with analysis. But before we go to analysis, I just want to pop up a few of these designs that the text brought up. You don't need to know all of this in detail. Just be familiar with the words and know that they are experimental designs. You don't need to memorize all of these steps or anything. Just if you ever hear somebody saying, oh, I'm doing a pretest post-test equivalent groups design, you'll know that's an experimental design. And to read these, the R over here is usually random assignment is what it means. The X's are the treatments, and the O are the observations. And the numbers are which time they did the observation. So this is they did their first observation, their pretest. They did the treatment for each. So this is one group, and this is the second group. They did their post-test, which is the second one here, and then they're going to analyze it. But you guys don't need to worry about that for right now. What we do need to consider, perhaps, is internal and external validity. So if you have some questions, I don't want this video to be too long, so if you have some questions about how that affects your study, we will go back to that a little bit later. Check out that video on the Moodle page. Until then, let's talk about that analysis. So when we're analyzing quantitative data, we use our statistical methods. And our statistical methods, this is another area that few individuals had trouble with. We have our descriptive methods and we have our inferential methods. Our descriptive methods are those things that are describing our group. We're not really making comparisons. We're not trying to say that one is significantly greater or less than the other. We just want to describe it. So if you were doing a study of students and you gave them a survey and you're collecting all that information, you would, for your descriptive statistics, you would maybe talk about what is the average GPA of the students that answered your survey. What percent were female? What percent were male? What percent were African American, Caucasian, Hispanic, Asian American? What percentage maybe were freshmen or seniors? You're just describing them. We're not trying to say that one scored better than the other. We're not doing any test really. We're just running our averages and our frequencies and doing that descriptive side of it. Now when we go to inferential methods, our inferential statistical methods are making inferences. This is where we're making predictions and coming up with our conclusions about how our variables are interacting with each other rather than just describing things. So you see down here it says significant tests, confidence intervals. Your inferential methods are like your t-tests, where you're comparing two different averages to see if they are statistically significant. Looking at the Canada example a minute ago, or the recall one that we were looking at, and one group got 100, one group got 95. Yeah, at face value, 100 is worth more than 95, but is that really statistically significant? Or was it just by chance that we got those two numbers? So this is where we do that work. All of our analysis, like our ANOVAs, and moving on into correlations later, all of those will be in inferential statistics. So your descriptive methods will probably look the same whether you do a correlational study, an experimental study, whatever you're doing, those descriptive methods are going to look pretty much the same, if not identical. The inferential part is going to change because what you're trying to predict or say is going to be a little different. If you're doing correlations, it's going to be correlations and regressions and that type of work. If you're doing a comparison of two things, like an experimental design, you're going to be doing t-tests and ANOVA. And to help break that down a little bit, I'm sorry this is a little bit cloudy again. This is somebody else's images I'm just using to take us through this. These are for our experimental design. So you'll see independent t-test, paired t-test, one-way ANOVA. If we have, and it'll tell you the dependent variable, one parameter, independent variable, and it'll tell you what it works with, two unrelated levels, with two related levels, with two or more unrelated levels, and it'll give you an example of a case. I will upload this slide deck onto our module page so you can look at this to kind of help you break that down, but just to give you an idea of how many variables you have and what you're looking at affects which statistic that you're going to use, whether it's an ANOVA or a t-test or whatnot. This is where that really tedious section on statistical analysis in the experimental design chapter will help you. You just need to make sure that whatever statistic you pull here, the t-test or the ANOVA, that whichever design you're doing here fits the type of data you have. Does it fit the dependent and independent variables that you have here? Does it fit the kind of design that you're doing? So that's it for a very quick overview of experimental designs and analyzing that data. Next we'll do correlational designs, but if you have any questions, do let me know.